want to thank the rest of the organizing committee and IPAM for hosting this wonderful program that has been very interesting so far. And I want to start this workshop with giving my perspective of why machine learning is important for us, for what we are trying to do. And I'm not sure I'm going to talk about interpretability much, but it's something we would like to do. So if you have suggestions on how to interpret the machine learning we use, I would be very interested in discussing that. Okay. In my group, we are interested in biophysical systems, and we are interested in modeling biophysical systems, mostly molecular biophysics. And in molecular biophysics, in biophysics in general, but as I said, we are focused on molecular biophysics, there is the problem of very broad range of length and time scale that are interconnected. And historically, different methods have been developed to target different resolutions, because it's very difficult to do the multi-scale modeling. I mean, there are works trying to attempt the multi-scaling, but bridging the whole range of scales from atomic to cellular level is basically impossible right now. So different methods have been developed to target different resolutions, and for instance, at the finest level, quantum mechanics is used to study chemical reaction, for instance, or coupled with the molecular mechanics, QMMM, to study enzyme reactions, very localized and very fast processes. Molecular dynamics is used more in general to study protein systems that are reasonable size, like medium-sized protein. Right now, it's possible to do folding and unfolding of proteins that is up to milliseconds with tricks, microseconds with brute force, and milliseconds with certain tricks. And but it's not possible to go farther. To study slower processes and larger systems, one has to develop some sort of coarse graining. And the extreme scale, the extreme level, coarse graining means you can go up to study cellular processes, you can go up to one protein represented by a bead, and this way you can study protein-protein interaction and things like this in the whole cell. And this is called a reaction diffusion simulation that has been developed independently. What we're interested in my group is try to bridge this resolution, to try to develop methods that are in between, so that we can connect atomic level studies with cellular level studies. And when we talk about coarse graining, we may mean different things. We can do coarse graining in different spaces. One kind of coarse graining is coarse graining in conformation space. And what I mean by conformation space is the space spanned by the whole configuration of the system. So if we have n atoms, is 3n degrees of freedom, is the 3n dimensional space that is describing the system. Each point in this space is a configuration of the molecule with n atoms. And this is a very high-dimensional, a very complex space. And what we would like to do is to reduce it into, partition it into parts, into regions, such that each region is biologically meaningful. It can be, for instance, the folded state of the protein, the unfolded state, a functional state. So we would like to partition it into metastable region with a certain probability of being in each region and probability of transition between the region. And this is one sort of coarse graining. It's more like coarse graining in time, if you want. But the coarse graining I'm going to talk about today is coarse graining in structural space. That means you have the structure of the molecule that is in 3D, and we want to group the atoms. So this again is a large number of atoms, can be like thousands, and we want to group together groups of atoms into representative beads, and such that the resolution of the system is lower and is easier to study, to simulate and to study what's going on. But we want to do it in a way that we preserve some property of the whole system. Okay? Of course, we cannot do it randomly. About the first coarse graining, the coarse graining in time, we have worked on that for a number of years, and I don't want to talk about it today, but if you're interested, that we wrote a review a couple of years ago with Frank about the state of the art of theory and methods and open problems in this kind of coarse graining, that is finding the representation. In this case, this is BPTI, that is the largest protein, and this is the representation in this coarse resolution, meaning this is the three states, the three functional states of this protein in the folded configuration, and these are the time interconnecting the states. But as I said, what I want to talk about today is coarse graining in a structural space. So finding a way to represent a complex molecule with many atoms into a set of beads, interacting beads, and with an energy function that can reproduce the same physics of the original system. There are different ways to do that. This is from a review that Will Noyd wrote a few years ago. I have stolen this image because it represents the idea very well. There are several ways to do coarse graining. It depends what you want to preserve, because you are reducing the dimensionality of the system. You cannot preserve everything. You need to decide what is that you want to keep of the system of interest. If you want to if you want to start from a fundamental description, you can do a bottom-up to coarse graining. So you want to start from an atomistic model and do some renormalization of the degrees of freedom to go into some coarse-grained model. Or you may go top-down. You may want to preserve experimentally measured quantity, macroscopic, for instance, ensemble averages, or some thermodynamic properties. And in this case, you go down from averages into the coarse-grained model. Or you may want to start with what is called knowledge base. That means, or is also called a structure-based model, that you want to start from some experimental determinate structure. For instance, you want to make sure that, for instance, if you have a protein, it's going to be folded in the configurations, it's the folded state. And you can use some physics in order to make this work. And again, to give you an idea how this works, this is what is called the structure-based model. You take the structure, the folded structure of a protein, and you consider only, in this case, only the carbon alpha as representative beads, and you construct a polymer stringing together the carbon alpha, and this is your coarse-grained model. And then you have to associate an Hamiltonian energy function such that you reproduce some property of the original system. And in the structure-based model, you only you make these ansatz. You assume that there is an interaction, an attractive interaction of some sort. In this case, is 10-12 potential, but it's not the only choice, between beads that are going to be in contact in the native state, and then local terms to model the local geometry, like the steric interactions. And as I said, attractive interactions between beads that are going to be in contact in the native states. This choice is motivated by some results, some statistical mechanics results, known as the minimal frustration principles, that postulate that proteins have evolved to minimize frustration, such that overall this is what you should expect on average, even if there are multiple interactions in even non-native contacts interact during the folding. This is on average what you should expect for the dynamics of the system. This is a very crude model, but it works as a first approximation. This is some recent work we did in the last few years on studying the snare complex, that is this protein complex that is important for the fusion of a vesicle with the membrane that is important for neurotransmission. We studied the folding and unfolding of this large protein system with, upon application of force with this structure-based model, and we were able to reproduce several experimental results. This is the force extension curve. This is the force upon separation of the two termini applying force, and we found 7 states for this system, and we were able to connect these states with experimentally observed results, and so we could, with this model, we were able to reconcile several different experimental results for this system, and this is a starting point for more accurate studies. This is just a first level, first order approximation to start with more refined study on this, for instance, on these different intermediate that we find for this system. So, but if we want to do something more accurate and more rigorous, there are several questions we need to address. For instance, how do we pick the coarse variable? How do we do this grouping of atoms into beads? This is a question that doesn't have an answer. In the first workshop, we heard about some autoencoding to try to define the coarse variable automatically. This is still an open question, and we are also working on this. Then, when you have defined the coarse variable, you have to define the energy function and the dynamics equation to reproduce the system of interest. And then, also, we would like to define methods to incorporate experimental data. So this would be the bottom-up approach, starting from an atomistic description. We want to define some renormalization into an effective energy functions, and this would be the top-down approach using experimental data, and ideally we would like to combine all of these. Mostly I'm going to tell you about the second point and the third point too today. Oops. So for the first point, this is what is called the coarse-grained mapping. We have an atomistic, this is some notation, we have an atomistic representation. R is a point in 3n, where n is the number of atoms, and we do a dimensionality reduction to lowercase n, that is the number of beads that we are going to consider. Lowercase n is going to be smaller than capital case N, hopefully much smaller. And this is the mapping. Usually we use, for this kind of models, use a linear mapping. So we use some linear combination of the coordinates of the atomistic representation to find the coordinates for the coarse-grained representation. For instance, we can take the center of mass of the bead, of the atoms we are considering in a bead, to be the effective interaction center for the coarse-grained bead. We have an atomistic potential that is given by first principle, for instance, from quantum mechanical calculation, already finding a force field is atomistic potential. This is a classical atomistic potential. This is also an open problem, but we assume this is solved, and there are machine learning methods to find this atomistic potential. So we take this as a given, and we want to find a CG potential, a coarse-grained potential that represents our system in the coordinate, the coarse-grained representation. So this is just an illustration. We have a group of atoms that goes into an effective bead through the mapping operator. Yes?
So I understand going from capital N to lowercase n is this coarse graining, but I'm a little confused why it's necessarily 3. Like, why do you need to think of it as a bead and not like some kind of something with a moment of inertia or, you know?
Because we would like to keep some physical representation of the system, so we would like to interpret it as a polymer.
No, but I mean when your coarse grained thing is just a dot, right? It just has location.
Yes.
It could be like a blob with some low multipoles, like a moment of inertia tensor or something like that.
Yes, yes. This is the easiest thing to do. We could do it more complicated. Yes.
Okay. But do people do that, or it's almost always like?
It's almost always like this. Because then you want to write, and I'll show you later, but usually people take this CG potential in the same functional form of the atomistic potential, just changing the parameters. And this is, and I'll show you that doesn't work. We need to change the functional form, and we are using machine learning for that. But I mean, I would be happy to discuss this further. So, what do we want to preserve when we do the coarse graining? What are the properties of this coarse grain potential that we want to find? One way to do coarse graining, one way to find this potential is through thermodynamic consistency. And what I mean by thermodynamic consistency is that the free energy of the system, the free energy of the coarse grain model should be the same as the free energy of the Olathoe model. So this is the definition of free energy. So we want basically we want the probability of finding the system in one state the same in both models. We need to define what one state is, but if we have the same part of the space, we want the probability with the two systems to be the same, assuming that the probability, what the thermodynamic given by the atomistic representation is the correct one. So this is the definition of thermodynamic consistency. So this is the Olathoe potential, the atomistic potential, V of R. This is the definition of probability in terms of the coarse grain coordinate. This is the probability of observing the coarse grain coordinate in configuration X, given by the atomistic representation. And we want this probability to be consistent with the effective energy function for the coarse grain coordinate. So in a sense, this is fixing the coarse grain energy function. If we want the thermodynamic consistency, the coarse grain energy function is given. The problem is that this is the formal definition, but it's impossible to calculate it in practice, because through this integral you get a lot of, even if the atomistic potential contained only pairwise interactions, through this integral you get a lot of multi-body interactions characterizing this thermodynamic consistency. What kind of multi-body interaction is, we don't know, because we cannot do this integral exactly. So this is a question we would like to address. This is how it works for a trivial system. So this is coarse graining from 2D in 1D. We have that the atomistic system is this two-dimensional system with two deep minima, and the interesting dimension here clearly is the x-coordinate. So we coarse grain away the y-coordinate, we project onto the x-coordinate, and in this case we can do this integral exactly, and this is what we get for the coarse grain potential. So we want to do this instead from then 2 to 1, from like millions or thousands of degrees of freedom into a handful. So because we know what we want, it's just that we don't know the functional form. This is a good case for machine learning. This in particular is a good case for using neural networks. In particular, it's possible to reformulate the thermodynamic consistency into this so-called force matching that is equivalent to this the minimizing of this functional. Basically, it's possible to reformulate it in a variational form. It's possible to show that the potential U, the coarse grain potential U that satisfies thermodynamic consistency also minimizes this functional. If we find the potential that minimizes this functional, this is the so-called potential of mean force, such that the force on the coarse grain coordinate is the average of all the atomistic forces on that coarse grain representation. this again is something that we cannot compute in practice, but what people have been doing so far is to use explicit functional form for u with a lot of parameters, and then find the parameters minimizing this functional. And this functional, this f of r are the instantaneous atomistic forces. So assuming you know the atomistic forces at each configuration of the atomistic system, you can find the gradient of the potential, that is the potential, by minimizing this functional. But you need to have a functional form for u. And this is the problem. We don't have a functional form for u. So we thought that this is a perfect case for machine learning, because we can approximate, we can use a neural network as a universal function approximator, and we can, instead of fixing a functional form for u, we can use a neural net here. And okay, we did some additional work to show, that it's possible to decompose this functional into terms like bias, noise, and variance. But if you're interested, I can point you to the paper.
Question?
Yes.
What is theta?
What is?
Theta. Are those the
These are the parameters of the model, the parameter of the network. In general, you can have whatever parameters you want into the functional form of the coarse-grained potential. In this case, what we're going to do, the potential is approximated by a neural network, so theta are the parameters of the network. So this is what we came up with. This is the so-called CG nets. So we start from the coarse-grained coordinate. X are the coarse-grained coordinates. So we have a mapping, a coarse-grained mapping, and X are the coarse-grained coordinate. And we want to find an energy U of X for this system. And we have the forces, we have the Olathoe coordinates and the forces for an ensemble of configuration, a Boltzmann ensemble of configurations for the system. We go through a fissurization layer that is very important to introduce rototranslational invariance, because we want our energy function to be rototranslational invariant, because we want the energy not to depend on the position of the system or rotation of the system around the center of mass. This is a physical requirement. So we enforce this by taking the energy function as a function of only internal coordinates, like distances and angles and dihedrals. Then we divide the energy in two parts. One part is the prior energy, that is extremely important, as I'll show you in the results. And here we enforce all the physical constraints we know of the system. For instance, the fact that this must be a polymer, so the beads are joined in a string. There are bonds between bead I and I+1. The fact that two beads cannot occupy the same point in space, there is an excluded volume, and all the static constraints we know. And in principle, you could use anything here, like you could even use a different energy function obtained with some other method, some naive energy function for the system that enforces the asymptotics, like the fact that you cannot overlap two beads and things like this. And then the rest, that is basically all the multi-body interactions we don't know, we put them into a neural network. Then we use the total energy, we take the gradient and to find the forces, and we put the forces into this loss function that we minimize. Yes?
So theta is not the parameters of the coarse-grained nodes, it's the raw parameters of nodes?
Theta is the parameters of the network.
Oh, okay.
Or the weights of the network.
So only the positions enter the energy?
Yes. Yes, theta is what you optimize for. This is the loss function that depend on the parameters of the network and the position, but then you average over all the positions. Yes.
So just to make sure I understood, you have a simple model which is the prior model, and you have a gradient from that, and then you have the gradient. The other part of the gradient is from the difference, the multi-body interactions that you add.
So you sum these two parts. The gradient is the gradient of the sum.
Yeah, so the gradient of the
Yes,
sum. So
yes.
you have a gradient of the kind of simple prior model.
Yes.
And a gradient of the multi-body interaction.
Yes.
And-
Yes.
Sorry, just one, you have X's and R's. Earlier, your notation was that X was like coarse-grained and R was, here, I don't,
No, R here is the coarse-grained, sorry.
okay, so in the input here, it's all the coarse-grained.
Yes, yes,
And this-
yes.
Somewhere in there, you also have, so that the fine-grained picture never enters.
Here is this F of lowercase r, these are the atomistic forces. This is the fine-grained forces. So you project the fine-grained forces on the coarse-grained coordinate with your mapping, and you take the difference between the instantaneous difference between this projection and your gradient.
And that capital F you have previously from something
Yes,
outside.
you do, for instance, some sampling of the atomistic system, and you save the configuration and the forces. This is a limitation, the fact that you have to use forces, and we are working to find alternative loss functions for this, because if you have to do a long simulation of the system, the atomistic simulation of the system, and save forces, is already a lot of effort to define the coarse-grained model. Yes.
When you're projecting the forces into the coarse grain, that makes sense, right? Because like the coarse graining is defined on the R's, but here the coarse graining is over the forces. But you're just like, it's like how does that work exactly?
So let's say you take the coarse-graining mapping is you have a group of atoms and you take the center of mass.
Center mass. Okay, so it's just like some.
Yes, you take the forces with the same weight. Or if what we do in what's going to follow is we do like a decimation. We take one bead to represent, one atom to represent the coarse-grained bead. In this case, you just take the force on that atom.
Okay.
Yes.
I was curious, if you don't coarse grain and you use this method, do you recover beta?
In this case, it's exact. If you don't coarse-grain, this F is the gradient of the potential.
Well,
Instantaneously.
you still use a neural network to try to solve that.
So we have done it for a test system, not for the full atomistic system, but we have done it for toy systems, and then you do. Yeah, you do it. But it's just a definition of, it's just a test of the neural network, because it's just a definition of the force. If you don't have any coarse graining, the force is the gradient of the potential, minus the gradient of the potential. Other questions? Okay. Oops. Okay, let me show you how it works for a 2D toy model, the same toy model I've shown you before. So this is coarse graining from 2D to 1D. So we use this force matching with coarse graining is the x coordinate, and this is what we find. This is the instantaneous force, are the orange points, and there is a lot of noise because for the same coarse-grained coordinate, for the same x coordinate, there are many y coordinates that are consistent with it. So the instantaneous force is a distribution around it. But if you minimize this functional, you find the exact coarse-grained force. So in this case, we know what is the exact coarse-grained force because we can do the integral analytically. And this is to show you that if we don't, here regularized means without the prior energy. In this case, the prior energy is a confining energy. It's like an harmonic restraint to keep the system confined. And this is the physical prior we know for these systems. If for a protein would be the fact that there are bonds, and the fact that there is a forbidden space that in the system that you cannot explore. And if you don't use the prior energy, if you don't regularize the CG net, in regions where you don't have points, the network is completely wrong. This is the CG net without regularization, the green curve. Where there is no point, the network doesn't know what to learn and goes into a completely wrong force. The correct force is the red one. And this is for the force, this is for the potential. This is just the integral of this. So the correct one is the red. And if you don't use the regularization, this prior energy, you go to something completely wrong. This depends on the activation function that you use, of course. But in this case, I think we use the tangent activation function, and you go to a constant force if you don't use, to a constant energy if you don't use any regularization. So at this point, we can apply to a real molecule. The first example was on alanine dipeptide. That is the workhorse for all these kind of models. This is always the simplest molecular system you can come up with. And the coarse graining is from an hydrated alanine dipeptide. So this is the molecule with 22 atoms. And then there are all the water molecules around. So even if the system is simple, it's already thousands of degrees of freedom because you have all the water molecules. And we coarse grain it into 5 beads, just the backbone atoms of this molecule. So we go from thousands to 15 degrees of freedom. And these are the different architectures. This is the CG net that I showed you. And we compared with the unregularized one without the prior energy. And we compare with the state-of-the-art in coarse graining that is using only two-body interactions. And to model the two-body interactions, we defined in the most general form, we defined a neural network, or we call it spline unit, for each two-body interaction. So it's the most general two-body interaction potential. And these are the results. This is the ground truth. This is what you get from, this is the free energy. So remember, in the thermodynamic consistency, we want the free energy to be the same. So the test is if we can reproduce the free energy of the system projected on certain collective coordinates. This is the Olathoe model. So this is the free energy as a function of the two dihedral angles. So you have these two dihedral angles centered around the carbon alpha. And, okay. This is what happens if you use only two-body interactions, if you don't consider the multi-body interactions. You kind of get these 4 minima, but you completely miss these shallower minima, number 6 and number 3, and you create some spurious minima here. So this tells you that multi-body terms are essential. This is as far as you can go with two-body only interactions. This tells you that there is the need of multi-body interactions for a coarse-grained model to work, even if as simple as an anidipeptide. Remember, this also coarse-grained the water, so this is taking into account also the water-effective interactions. This is what we get if we don't regularize it, if we don't use the prior energy, and you get the minima, but then the network can go everywhere, even in regions that are forbidden in a physical space. For instance, you can overlap beads, you can strain bonds and stuff like this, while if you use this prior energy, you get the correct minima and the correct shape for the free energy. And and if you do molecular dynamics, this is obtained doing molecular dynamic simulations with coarse-grained energy. So we can simulate the system with the coarse-grained energy and reproduce the same free energy. And if we take samples of structure from these different minima, from 1, 2, 3, 4, 5, 6, in this coarse-grained representation, and we overlap them with the Olathoe representation, they are identical. So really, we sample from the same distribution. Then we tried something more challenging, that is the coarse graining of a small protein, and this is signaling. We don't want to do folding and unfolding of this protein. So this is a small protein, but still is exhibit folding and unfolding. So we took, this is 10 residues, that is already hundreds of atoms, and in water, so this is again several thousand degrees of freedom. We coarse-grain it to 10 beads, considering only the carbon alpha without water, so we go from 1,000 to 30 degrees of freedom. And again, we compare the CGNet model with this prior energy. It's very important here to include the repulsive interactions for the excluded volume in order to avoid overlapping of beads. And we compare it with two-body interactions only. And again, we find that this is the ground truth. We project the free energy into collective variables that represent the slowest motions of the system. Theta coordinates are called. And this is the ground truth. This is a folded minimum A. There is unfolded minimum B, and the misfolded state C. And if we use only two-body interactions, as you can see, you don't find the folding unfolding transition. There is just a blob that is in between the folded and unfolded. While if we use the CGNet, the regularized CGNet, we find the folded, unfolded, and misfolded minima. So we can reproduce the overall folding, unfolding, misfolding of this process. And this is projected in 1D basically in the folding, unfolding coordinate. And indeed, you find that the neural network potential finds the two folding and unfolding minima, while the one without multi-body energy doesn't find anything. And again, if you take samples of structures from the three minima, they overlap very well with structures from the Olathoe model. So we think that this shows that the coarse graining can be formulated as a machine learning problem. And in particular, neural networks are crucial to capture multi-body effects because we don't have a functional form for it. What we would like to do now is to try to use the fact that we can capture this multi-body effect to try to understand what these multi-body effects are. And this is a very challenging problem, but we are trying to work on it. And application to more complex systems may require more physical constraints, and we are working on this too. And of course, all of these, what I showed you is to reproduce the thermodynamics of a system for which we have already the Olathoe model. But what is more interesting, for which we already have the Olathoe simulations, but we don't want to run Olathoe simulations to find the coarse-grained model because they defeat the purpose. We would like to have a coarse-grained model instead of Olathoe simulation. So we would like to design transferable coarse-grained model. That means to design coarse-grained model on small system and then use them to simulate large system for which we don't have Olathoe simulations. But there is another problem. That is the dynamics. So what I showed you is the thermodynamic consistency, meaning that we can reproduce the same distribution, but doesn't say anything about the dynamics, how you go from one minimum to the next. And if we analyze the dynamical modes of the signaling system, this system I showed you here, I already see here that this minimum is comprised of many different minima. Overall, this is a minimum and reproduces the folding and unfolding, but if we look at the dynamics inside here, it's different from the dynamics inside this minimum. And in fact, if we do this basically, if we look at the collective dynamical modes of you can think of this as some sort of nonlinear modes of the system, the slowest mode of the system. This is for the original Olathoe. You have where you project the free energy on these the first and second slowest modes. But this is what happens if you do it for the CGNet dynamics. You find the same folded state, but the unfolded state spreads out into many different subminima. And this is if you do it for the first and third. Again, you find many subminima. So what if we want to coarse grain also enforcing dynamic consistencies, not just thermodynamic consistency? So this is thermodynamic consistency. This is the general form of the force matching that I showed you before. This is the kinetic consistency. In kinetic consistency, what we would like is to preserve these slow modes. In addition of preserving the thermodynamics, we would like to preserve the slow modes that are given by the eigenfunctions and eigenvalues of the dynamical operator acting on the system. And so we would like, if we know the slow modes, we would like to design a loss function that preserves the slow modes. And this is an example on we need to know what the dynamic of the original system is and what the dynamic of the projected system is, assuming, we can assume that it's an overdamped Langevin equation. We can generalize it, but assuming here is an overdamped Langevin equation with a constant diffusion constant. The generator of these dynamics is given by this operator here, where d is the diffusion constant, and there is the gradient of the potential here. So we want the eigenfunction of this operator to be the same in the original system and in the coarse-grained system. So we can design a loss function to enforce that, because we know the generator. Now the potential enters the generator. So in the loss function, again, the potential is what we are optimizing. So we can, this is what we call spectral matching. Instead of enforcing thermodynamic consistency, or in addition to enforcing thermodynamic consistency, we can enforce kinetic consistency by trying to match the eigenfunctions of the dynamical operators. And this is just plugging in this generator here. This is what you get for the overall loss. So you need to know the eigenfunction of the original system. Instead of the forces here, there is no forces of the original system or the fine-grained system required, but you need to know the eigenfunctions and the eigenvalues. The eigenvalues give you the time scale, and this you can preserve the slow modes and the time scale. So yeah, as I said, so this is what you optimize. And what you need to know is the spectral data, that means the slow modes of the original system. This is in a weak, the weak form of this spectral matching. We project it on some test function that is just for numerical stability. So we need to select a set of test function, but this is not important. It's just technical.
Question, Cecilia?
Yes.
If you already know the slow modes of your original system, so that you can do this kind of matching, isn't that mostly what you want? I mean, isn't that also kind of assuming you have the answer you mostly?
Yes, but you want to do it in a transferable way. Eventually, you want to do it for small system.
Oh, I see.
To find some so we would like to design a network with some parameter sharing. So that you can decompose it into either functional groups or interactions between different residues, so you can do it for a larger system. Of course, this is a big question, how much, what kind of transferability you can have, and which model you need for transfer. So this is a whole big question, but this is the final goal. This is how it works for a toy model. So this is, we consider this three well potential. We perturb it with noise. So this is the original system. This is perturbed. And here, if we do spectral matching here, we expect to recover only the slow modes. And indeed, this is the potential you find doing spectral matching. You recover the slow modes, that is the transition between these deep minima. You don't care about the fast modes that are the oscillation in this perturbed potential. So it works. This is just a proof of principle. At this point, I'm going to show you some results that we obtained with some linear regression at this point. Where am I? Okay, we can do also something else. Instead of, okay, here. instead of changing the potential, we can say we get the potential by force matching, enforcing thermodynamic consistency. Then we can change, we can use this to learn the diffusion coefficient. We can say that now we can take a diffusion coefficient that is position dependent to recover the dynamics. Instead of changing the potential itself that we already obtained with force matching, we can modulate the diffusion coefficient with spectral matching to learn the dynamics. And this is what we get here. This is just the technical details, but again, what this says, this is just using a linear model. We are now using a neural network for this as well, like similar to CGNet. But this is, if you use a linear model, you end up with the regression for the diffusion coefficient. And this is what we obtain. This is for this, again, a toy system, but is a challenging system because we introduced, so there are these minima, and we introduced this large barrier here, and we project onto 1D. And this one barrier, 1D, the x coordinate is not the best to reproduce the transition between these minima, because this barrier is spread along the y coordinate. And but so if we do coarse matching, we miss the dynamics completely. And this is the time scales that we get. The reference is in black. The force matching time scales are given in red, and they're completely wrong. We invert the first and second slope processes. But if we use this method, if we use spectral matching, we recover the time scale and the dynamical mode of the system. So we think that this can be, and this is for alanine dipeptide. This is with coarse-grained alanine dipeptide. In this case, it's the molecule I showed you before. We coarse-grained it just in two coordinates that are these two phi-psi dihedral angles. And this is the potential we obtain for force matching that I showed you before. And this is the diffusion that we obtained with the diffusion constant that we obtained with the spectral matching. And combine the two things, so this is the reference, again, the reference time scales are in black. The spectral matching, the force matching time scales are in red. And using this corrected diffusion, we can simulate the dynamics of the system, then we can recover the correct time scales. So this is combining spectral matching and force matching. But in principle, this could be used instead of force matching to find the potential that in this case does not require the forces. Requires to know the eigenfunctions, but sometimes the eigenfunctions can be found just with a sampling, sampling of the system.
Happening if you use only the first eigenfunction, that
you get only the first time scale.
that's equivalent to the force matching.
No, force matching gives you the minima, but doesn't tell you anything about how you go from one minimum to the next. Yeah, if you do force matching, for instance, for we are doing it now for signaling, but in principle, if you do force matching, spectral matching for signaling only with the first eigenfunction, you don't know anything about the dynamics inside that minimum, so you can find the same results, I guess, as force matching. Okay, I think I don't have time to talk about anything else, so I wanted to tell you something about the incorporation of experimental data, but just in one slide, we are also designing some machine learning method to use experimental data in experimental observable like fret distribution or NMR data to tune the parameters of a coarse-grained model. And this eventually we would like to do this in addition to force matching and spectral matching. And the formulation we have right now is using a maximum likelihood approach, basically to define a likelihood of the coarse-grained model to reproduce certain experimental data, and then to change the parameters to maximize this likelihood. And this is published, and we are working on a new set of experimental data, and if you're interested, I can tell you later.
We had quite a bit of discussion, so you could take any
Okay.
thoughts, but yeah.
So let me show you. Okay, the way we do it, we start with the experimental measurements and uncertainty. And this can be, as I said, for instance, fret. Fret is a way to measure the distance between two probes in a molecule as a function of time. So what you get is a distribution of the distances. For instance, in this case, is the distribution of the distance between two specific locations in a protein at equilibrium. And we want to reproduce this, or we have NMR observables like things that probe the distribution of side chain orientation locally, or things like this. So what we do, we have a model Hamiltonian, and the initial model Hamiltonian, initial parameters, and this can come up from, again, from spectral matching or whatever. This is an initial Hamiltonian that we want to correct to reproduce experimental data. We simulate the system with this initial Hamiltonian, and we predict experimental observables. Those E are the corresponding observable but predicted in simulation, where F are the experimentally measurable observable. So we have a functional form, we have a way to measure the observable in simulation. And then the whole point is in defining a likelihood for the model, for the simulation, to reproduce the experimental observable. And we model this likelihood as a product of Gaussians centered on the experimental observables with the variance given by the experimental uncertainty, and we measure the Gaussians on the simulated observable. So if the experimental observable are the same as the simulated observable, the Gaussian is 1. So it's maximum, the likelihood is maximum. If they are much more different than the experimental uncertainty, the likelihood is close to 0. And we take...
I have a question. So when you make this algorithm work, your experimental observable should be your forward model for the experiment should be exact, or it can be a proxy model. So exact means that if you know your configuration, you can predict the experimental signal exactly, or there can be some off parameters.
There can be parameters. In fact, this is, for instance, for fret, you have to model also the fact that you have a probe.
Okay.
And so this is also something you need to take into account.
Also the parameters related to experiment.
These are, in what I'm showing here, these are maximized separately. These are optimized separately before you use it some test system. Okay. Before you put it in here. Otherwise, there are too many parameters. In principle, you could do everything together, but otherwise, there are too many parameters. And the trick here is to be able to express the likelihood as a function of the model parameters. If you can do that, you can maximize the likelihood. You can change the parameters to maximize the likelihood. And just to show how it works, this was to design a coarse-grained model to reproduce an Olathoe simulations for this protein. And for instance, in this case, we found that we were able to compare, because we have a likelihood, we can compare the likelihood of different models. We use the C-alpha model, only the carbon alpha to represent the protein, or carbon alpha, carbon beta, and we found that in this case, a carbon alpha model is not a good way to represent the system, because the likelihood goes to 10 to the minus 6, converges to 10 to the minus 6, while for a carbon alpha, carbon beta, we can go to a likelihood close to 1. And more recently, we are doing this with NMR data, using ubiquitin as a model system. Again, as a carbon alpha, carbon beta model, we use J coupling parameters, 63 values obtained from experiments, and we can correct the dynamics. We can use a coarse-grained model again to reproduce the dynamics of the system as given by NMR data. And with this, I would like to thank The people who've done the work mostly have talked about the work of Zhang, who's here, and Nick, who's here, and Felix, and Irina is the latest thing I talked about, and Justin and Lorenzo also contributed to, were in my group before, contributed to this work. And thank you very much for your attention.